Hey, everyone. Hi, I'm Ashok. I lead the autopilot team alongside Milan. God, it's going to be so hard to top that Optimus section. We'll try nonetheless. Anyway, every Tesla that has been built over the last several years, we think has the hardware to make the car drive itself. We have been working on the software to add higher and higher levels of autonomy. This time around last year, we had roughly 2,000 cars driving our FSD beta software. Since then, we have significantly improved the software's robustness and capability that we have now shipped it to 160,000 customers as of today. Thank you. This did not come for free. It came from the sweat and blood of the engineering team over the last 1 year. For example, we trained 75,000 neural network models just last 1 year. That's roughly a model every 8 minutes. That's coming out of the team, and then we evaluate them on our large clusters, and then we ship 281 of those models that actually improve the performance of the car. And this pace of innovation is happening throughout the stack. The planning software, the infrastructure, the tools, even hiring, everything is progressing to the next level. The FSD beta software is quite capable of driving the car. It should be able to navigate from parking lot to parking lot, handling city street driving, stopping for traffic lights and stop signs, negotiating with objects at intersections, making turns, and so on. All of this comes from the camera streams that go through our neural networks that run on the car itself. It's not coming back to the server or anything. It runs on the car and produces all the outputs to form the world model around the car, and the planning software drives the car based on that. Today, we'll go into a lot of the components that make up the system. The occupancy network acts as the base geometry layer of the system. This is a multi-camera video neural network that, from the images, predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, balls, what have you, it predicts, if it's physically present, it predicts them, along with their future motion. On top of this base level of geometry, we have more semantic layers. In order to navigate the roadways, we need the lanes, of course. But then the roadways have lots of different lanes, and they connect in all kinds of ways. So it's actually a really difficult problem for typical computer vision techniques to predict the set of lanes and their connectivities. So we reached all the way into language technologies and then pulled the state of the art from other domains, and not just computer vision, to make this task possible. For vehicles, we need their full kinematic state to control for them. All of this directly comes from neural networks. Video streams, raw video streams, come into the networks, goes through a lot of processing, and then outputs the full kinematic state. The positions, velocities, acceleration, jerk, all of that directly comes out of the networks with minimal post-processing. That's really fascinating to me, because how is this even possible? What world do we live in that this magic is possible, that these networks predicts fourth derivatives of these positions, when people thought we couldn't even detect these objects? My opinion is that it did not come for free. It required tons of data, so we had to build sophisticated auto-labeling systems that churn through raw sensor data, run a ton of offline compute on the servers. It can take a few hours, run expensive neural networks, distill the information into labels that train our in-car neural networks. On top of this, we also use our simulation system to synthetically create images. And since it's a simulation, we trivially have all the labels. All of this goes through a well-oiled data engine pipeline, where we first train a baseline model with some data, ship it to the car, see what the failures are. And once we know the failures, we mine the fleet for the cases where it fails, provide the correct labels, and add the data to the training set. This process systematically fixes the issues. And we do this for every task that runs in the car.
Yeah, and to train these new massive neural networks, this year we expanded our training infrastructure by roughly 40 to 50%. So that sits us at about 14,000 GPUs today across multiple training clusters in the United States. We also worked on our AI compiler, which now supports new operations needed by those neural networks and map them to the best of our underlying hardware resources. And our inference engine today is capable of distributing the execution of a single neural network across two independent system on chips, essentially two independent computers interconnected within the same full self-driving computer. And to make this possible, we had to keep a tight control on the end-to-end latency of this new system. So we deployed more advanced scheduling code across the full FSD platform.
All of these neural networks running in the car together produce the vector space, which is again the model of the world around the robot or the car. And then the planning system operates on top of this, coming up with trajectories that avoid collisions or smooth, make progress towards the destination using a combination of model-based optimization plus neural network that helps optimize it to be really fast. Today, we are really excited to present progress on all of these areas. We have the engineering leads standing by to come in and explain these various blocks. And these power not just the car, but the same components also run on the Optimus robot that Milan showed earlier. With that, I welcome Paril to start talking about the planning section.
Hi all, I'm Paril Jain. Let's use this intersection scenario to dive straight into how we do the planning and decision making in Autopilot. So we are approaching this intersection from a side street, and we have to yield to all the crossing vehicles. Right as we are about to enter the intersection, the pedestrian on the other side of the intersection decides to cross the road without a crosswalk. Now, we need to yield to this pedestrian, yield to the vehicles from the right, and also understand the relation between the pedestrian and the vehicle on the other side of the intersection. So a lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that Autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal and lateral profile. Now, obviously, we are being a jerk to the pedestrian, and we would spook the pedestrian and his cute pet. We could have moved forward slowly, shot for a gap between the pedestrian and the vehicle from the right. Again, we are being a jerk to the vehicle coming from the right, but you should not outright reject this interaction in case this is only safe interaction available. Lastly, the interaction we ended up choosing: stay slow initially, find the reasonable gap, and then finish the maneuver after all the agents pass. Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far, because you will miss out on a lot of valid interactions. This basically boils down to solving a multi-agent joint trajectory planning problem over the trajectories of ego and all the other agents. Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem. It will be close to order of 10 milliseconds, even after a lot of incremental approximations. Now, for a typical crowded, unprotected lift, say you have more than 20 objects, each object having multiple different future modes, the number of relevant interaction combinations will blow up. The planner needs to make a decision every 50 milliseconds. So how do we solve this in real time? We rely on a framework what we call as interaction search, which is basically a parallelized research over a bunch of maneuver trajectories. The state space here corresponds to the kinematic state of ego, the kinematic state of other agents, their nominal future multimodal predictions, and all the static entities in the scene. The action space is where things get interesting. We use a set of maneuver trajectory candidates to branch over a bunch of interaction decisions, and also incremental goals for a longer horizon maneuver. Let's walk through this research very quickly to get a sense of how it works. We start with a set of vision measurements, namely lanes, occupancy, moving objects. These get represented as sparse abstractions as well as latent features. We use this to create a set of goal candidates, lanes again from the lanes network, or unstructured regions which correspond to a probability mask derived from human demonstrations. Once we have a bunch of these goal candidates, we create seed trajectories using a combination of classical optimization approaches, as well as our network planner, again trained on data from the customer fleet. Now, once we get a bunch of these seed trajectories, we use them to start branching on the interactions. We find the most critical interaction. In our case, this would be the interaction with respect to the pedestrian, whether we assert in front of it or yield to it. Obviously, the option on the left is a high penalty option. It likely won't get prioritized. So we branch further onto the option on the right, and that's where we bring in more and more complex interactions, building this optimization problem incrementally with more and more constraints. And the tree search keeps flowing, branching on more interactions, branching on more goals. Now, a lot of tricks here lie in evaluation of each of this node of the tree search. Inside each node, initially we started with creating trajectories using classical optimization approaches, where the constraints, like I described, would be added incrementally. And this would take close to 1 to 5 milliseconds per action. Now, even though this is a fairly good number, when you want to evaluate more than 100+ interactions, this does not scale. So we ended up building lightweight queryable networks that you can run in the loop of the planner. These networks are trained on human demonstrations from the fleet, as well as offline solvers with relaxed time limits. With this, we were able to bring the runtime down to close to 100 microseconds per action. Now, doing this alone is not enough, because you still have this massive tree search that you need to go through, and you need to efficiently prune the search space. So you need to do scoring on each of these trajectories. Few of these are fairly standard. You do a bunch of collision checks, you do a bunch of comfort analysis, what is the jerk and axle required for a given maneuver. The customer fleet data plays an important role here again. We run two sets of, again, lightweight queryable networks, both really augmenting each other. One of them trained from interventions from the FSD beta fleet, which gives a score on how likely is a given maneuver to result in interventions over the next few seconds. And second, which is purely on human demonstrations, human-driven data, giving a score on how close is your given selected action to a human-driven trajectory. This scoring helps us prune the search space, keep branching further on the interactions, and focus the compute on the most promising outcomes. The cool part about this architecture is that it allows us to create a cool blend between data-driven approaches, where you don't have to rely on a lot of hand-engineered costs, but also ground it in reality with physics-based checks. Now, a lot of what I described was with respect to the agents we could observe in the scene, but the same framework extends to objects behind occlusions. We use the video feed from 8 cameras to generate the 3D occupancy of the world. The blue mask here corresponds to the visibility region, we call it. It basically gets blocked at the first occlusion you see in the scene. We consume this visibility mask to generate what we call as ghost objects, which you can see on the top left. Now, if you model the spawn regions and the state transitions of these ghost objects correctly, if you tune your control response as a function of their existence likelihood, you can extract some really nice human-like behaviors. Now, I'll pass it on to Phil to describe more on how we generate these occupancy networks. Thank you.
Hey guys, my name is Phil. I will share the details of the occupancy network we built over the past year. This network is our solution to model the physical world in 3D around our cars. And it is currently not shown in our customer-facing visualization. And what you will see here is the raw network output from our internal dev tool. The occupancy network takes video streams of all our 8 cameras as input, produces a single unified volumetric occupancy in vector space directly. For every 3D location around our car, it predicts the probability of that location being occupied or not. Since it has video context, it is capable of predicting obstacles that are occluded instantaneously. For each location, it also produces a set of semantics such as curb, car, pedestrian, and road debris, as color-coded here. Occupancy flow is also predicted for motion. Since the model is a generalized network, it does not tell static and dynamic objects explicitly. It is able to produce and model the random motions, such as the swerving trainer here. This network is currently running in all Teslas with FSD computers, and it is incredibly efficient, runs about every 10 milliseconds with our neural net accelerator. So how does this work? Let's take a look at the architecture. First, we rectify each camera images with the camera calibration. And the images we're showing here were given to the network. It's actually not the typical 8-bit RGB image. As you can see from the first image on top, we're giving the 12-bit raw photon count image to the network. Since it has 4 bits more information, it has 16 times better dynamic range, as well as reduced latency, since we don't have to run ISP in the loop anymore. We use a set of reglets and FPNs as a backbone to extract image space features. Next, we construct a set of 3D position query along with the image space features as keys and values fit into an attention module. The output of the attention module is high-dimensional spatial features. These spatial features are aligned temporally using vehicle odometry to derive motion. Last, these spatial temporal features go through a set of deconvolution to produce the final occupancy and occupancy flow output. They're formed as fixed-size voxel grid, which might not be precise enough for planning and control. In order to get a higher resolution, we also produce per voxel feature maps, which we feed into MLP with 3D spatial point queries to get position and semantics at any arbitrary location. After knowing the model better, let's take a look at another example. Here, we have an articulated bus parked on the right side of the road, highlighted as an L-shaped voxel here. As we approach, the bus starts to move. The front of the car turns blue first, indicating the model predicts the front of the bus has a non-zero occupancy flow. And as the bus keeps moving, the entire bus turns blue. And you can also see that the network predicts the precise curvature of the bus. Well, this is a very complicated problem for traditional object detection network, as you have to see whether I'm going to use one cuboid or perhaps 2 to fit the curvature. But for our occupancy network, since all we care about is the occupancy in the visible space, and we'll be able to model the curvature precisely. Besides the voxel grid, the occupancy network also produces a drivable surface. The drivable surface has both 3D geometry and semantics. They are very useful for control, especially on hilly and curvy roads. The surface and the voxel grid are not predicted independently. Instead, the voxel grid actually aligns with the surface implicitly. Here, we're at a hill crest where you can see the 3D geometry of the surface being predicted nicely. Planner can use this information to decide perhaps we need to slow down more for the hill crest. And as you can also see, the voxel grid aligns with the surface consistently. Besides the voxels and the surface, we're also very excited about the recent breakthrough in neural radiance field, or NeRF. We're looking into both incorporate some of the nice NeRF features into occupancy network training, as well as using our network output as the input state for NeRF. As a matter of fact, Ashok is very excited about this. This has been his personal weekend project for a while.
About these NeRFs, because I think the academia is building a lot of these foundation models for language, using like tons of large data sets for language. But I think for vision, NeRFs are going to provide the foundation models for computer vision, because they are grounded in geometry, and geometry gives us a nice way to supervise these networks and frees us of the requirement to define an ontology. And the supervision is essentially free because you just have to differentially render these images. So I think in the future, this occupancy network idea where images come in and then the network produces a consistent volumetric representation of the scene that can then be differentiably rendered into any image that was observed. I personally think is a future of computer vision, and we do some initial work on it right now, but I think in the future, both at Tesla and in the academia, we will see that these combination of one-shot prediction of full volumetric occupancy will be the future. That's my personal bet.
Thanks, Ashok. So here's an example early result of a 3D reconstruction from our fleet data. Instead of focusing on getting perfect RGB reprojection in image space, our primary goal here is to accurately represent the world in 3D space for driving. And we want to do this for all our fleet data all over the world in all weather and lighting conditions. And obviously, this is a very challenging problem, and we're looking for you guys to help. Finally, the occupancy network is trained with large auto-label data set without any human in the loop. And with that, I'll pass to Tim to talk about what it takes to train this network.
Thanks, Phil. All right, hey everyone. Let's talk about some training infrastructure. So we've seen a couple of videos, 4 or 5. I think and care more and worry more about a lot more clips than that. So we've been looking at the occupancy networks just from Phil. Just Phil's videos, it takes 1.4 billion frames to train that network, what you just saw. And if you have 100,000 GPUs, it would take 1 hour. But if you have 1 GPU, it would take 100,000 hours. So that is not a humane time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we've built in-house 3 supercomputers comprising of 14,000 GPUs, where we use 10,000 GPUs for training and around 4,000 GPUs for auto-labeling. All these videos are stored in 30 petabytes of a distributed, managed video cache. You shouldn't think of our data sets as fixed, let's say, as you think of your ImageNet or something, with like 1 million frames. You should think of it as a very fluid thing. So we've got 500,000 of these videos flowing in and out of these clusters every single day. And we track 400,000 of these kind of Python video instantiations every second. So that's a lot of calls. We're going to need to capture that in order to govern the retention policies of this distributed video cache. So underlying all of this is a huge amount of infra, all of which we build and manage in-house. So you cannot just buy 14,000 GPUs and then 30 petabytes of flash NVMe and just put it together and let's go train. It actually takes a lot of work, and I'm going to go into a little bit of that. What you actually typically want to do is you want to take your accelerator, so that could be the GPU or Dojo, which we'll talk about later. And because that's the most expensive component, that's where you want to put your bottleneck. And so that means that every single part of your system is going to need to outperform this accelerator. And so that is really complicated. That means that your storage is going to need to have the size and the bandwidth to deliver all the data down into the nodes. These nodes need to have the right amount of CPU and memory capabilities to feed into your machine learning framework. This machine learning framework then needs to hand it off to your GPU, and then you can start training. But then you need to do so across hundreds or thousands of GPU in a reliable way, in lockstep, and in a way that's also fast. So you're also going to need an interconnect. Extremely complicated. We'll talk more about Dojo in a second. So first, I want to take you through some optimizations that we've done on our cluster. So we're getting in a lot of videos, and video is very much unlike, let's say, training on images or text, which I think is very well established. Video is quite literally a dimension more complicated. And so that's why we needed to go end-to-end from the storage layer down to the accelerator and optimize every single piece of that. Because we train on the photon count videos that come directly from our fleet, we train on those directly. We do not post-process those at all. The way it's just done is we seek exactly to the frames we select for our batch. We load those in, including the frames that they depend on. So these are your iframes or your keyframes. We package those up, move them into shared memory, move them into a double buffer on the GPU, and then use the hardware decoder that's only accelerated to actually decode the video. So we do that on the GPU natively. And this is all in a very nice PyTorch extension. Doing so unlocked more than 30% training speed increase for the occupancy networks and freed up basically the whole CPU to do any other thing. You cannot just do training with just videos. Of course, you need some kind of a ground truth. That is actually an interesting problem as well. The objective for storing your ground truth is that you want to make sure you get to your ground truth that you need in the minimal amount of file system operations and load in the minimal size of what you need in order to optimize for aggregate cross-cluster throughput, because you should see a compute cluster as one big device which has internally fixed constraints and thresholds. So for this, we rolled out a format that is native to us that's called small. We use this for our ground truth, our feature cache, and any inference outputs. So a lot of tensors that are in there. And so just a cartoon here, let's say these are is your table that you want to store, then that's how that would look out if you rolled out on disk. So what you do is you take anything you'd want to index on, so for example, video timestamps, you put those all in the header, so that in your initial header read, you know exactly where to go on disk. Then if you have any tensors, you're going to try to transpose the dimensions to put a different dimension last as the contiguous dimension, and then also try different types of compression. Then you check out which one was most optimal, and then store that one. This is actually a huge tip if you do feature caching. Unintelligible output from the machine learning network, rotate around the dimensions a little bit, you can get up to 20% increase in efficiency of storage. Then when you store that, we also order the columns by size so that all your small columns and small values are together, so that when you seek for a single value, you're likely to overlap with a read on more values, which you'll use later, so that you don't need to do another file system operation. So I could go on and on. I just went touched on 2 projects that we have internally, but this is actually part of a huge continuous effort to optimize the compute that we have in-house. So accumulating and aggregating through all these optimizations, we now train our occupancy networks twice as fast just because it's twice as efficient. And now if we add in a bunch more compute and go parallel, we can now train this in hours instead of days. And with that, I'd like to hand it off to the biggest user of compute, John.
Hi, everybody. My name is John Emmons. I lead the Autopilot Vision team. I'm going to cover 2 topics with you today. The first is how we predict lanes, and the second is how we predict the future behavior of other agents on the road. In the early days of Autopilot, we modeled the lane detection problem as an image space instance segmentation task. Our network was super simple, though. In fact, it was only capable of predicting lanes of a few different kinds of geometries. Specifically, it would segment the ego lane, it could segment adjacent lanes, and then it had some special casing for forks and merges. This simplistic modeling of the problem worked for highly structured roads like highways. But today, we're trying to build a system that's capable of much more complex maneuvers. Specifically, we want to make left and right turns at intersections, where the road topology can be quite a bit more complex and diverse. When we try to apply this simplistic modeling of the problem here, it just totally breaks down. Taking a step back for a moment, what we're trying to do here is to predict the sparse set of lane instances and their connectivity. And what we want to do is to have a neural network that basically predicts this graph, where the nodes are the lane segments, and the edges encode the connectivities between these lanes. So what we have is our lane detection neural network. It's made up of 3 components. In the first component, we have a set of convolutional layers, attention layers, and other neural network layers that encode the video streams from our 8 cameras on the vehicle and produce a rich visual representation. We then enhance this visual representation with a coarse road-level map data, which we encode with a set of additional neural network layers that we call the lane guidance module. This map is not an HD map, but it provides a lot of useful hints about the topology of lanes inside of intersections, the lane counts on various roads, and a set of other attributes that help us. The first 2 components here produce a dense tensor that sort of encodes the world, But what we really want to do is to convert this dense tensor into a sparse set of lanes and their connectivities. We approach this problem like an image captioning task, where the input is this dense tensor, and the output text is predicted into a special language that we developed at Tesla for encoding lanes and their connectivities. In this language of lanes, the words and tokens are the lane positions in 3D space. In the ordering of the tokens, and predicted modifiers in the tokens encode the connective relationships between these lanes. By modeling the task as a language problem, we can capitalize on recent autoregressive architectures and techniques from the language community for handling the multimodality of the problem. We're not just solving the computer vision problem at Autopilot, we're also applying the state-of-the-art in language modeling and machine learning more generally. I'm now going to dive into a little bit more detail of this language component. What I have depicted on the screen here is a satellite image which sort of represents the local area around the vehicle. The set of nodes and edges is what we refer to as the lane graph, and it's ultimately what we want to come out of this neural network. We start with a blank slate. We're going to want to make our first prediction here at this green dot. This green dot's position is encoded as an index into a coarse grid which discretizes the 3D world. Now, we don't predict this index directly because it would be too computationally expensive to do so. There's just too many grid points, and predicting a categorical distribution over this has both implications at training time and test time. So instead, what we do is we discretize the world coarsely first. We predict a heat map over the possible locations, and then we latch in the most probable location. Condition on this, we then refine the prediction and get the precise point. Now, we know where the position of this token is, but we don't know its type. In this case, though, it's the beginning of a new lane. So we predict it as a start token. And because it's a start token, there's no additional attributes in our language. We then take the predictions from this first forward pass, and we encode them using a learned positional embedding, which produces a set of tensors that we combine together, which is actually the first word in our language of lanes. We add this to the first position in our sentence here. We then continue this process by predicting the next lane point in a similar fashion. Now, this lane point is not the beginning of a new lane. It's actually a continuation of the previous lane. So it's a continuation token type. Now, it's not enough just to know that this lane is connected to the previously predicted lane. We want to encode its precise geometry, which we do by regressing a set of spline coefficients. We then take this lane, we encode it again, and add it as the next word in the sentence. We continue predicting these continuation lanes until we get to the end of the prediction grid. We then move on to a different lane segment. So you can see that cyan dot there. Now, it's not topologically connected to that pink point. It's actually forking off of that green point there. So it's got a fork type. And fork tokens actually point back to previous tokens from which the fork originates. So you can see here the fork point predictor is actually the index 0. So it's actually referencing back to tokens that it's already predicted, like you would in language. We continue this process over and over again until we've enumerated all of the tokens in the lane graph. And then the network predicts the end of sentence token.
Yeah, I just want to note that the reason we do this is not just because we want to build something complicated. It almost feels like a Turing-complete machine here with neural networks, though, is that we tried simpler approaches. For example, trying to just segment the lanes along the road or something like that. But then the problem is when there's uncertainty. Say you cannot see the road clearly, and there could be 2 lanes or 3 lanes, and you can't tell. A simple segmentation-based approach would just draw both of them. It's kind of a 2.5-lane situation. And the post-processing algorithm would hilariously fail when the predictions are such.
Yeah, and the problems don't end there. I mean, you need to predict these connective lanes inside of intersections, which it's just not possible with the approach that Ashok's mentioning, which is why we had to upgrade to this sort of.
Yeah, when it overlaps like this, segmentation would just go haywire. But even if you try very hard to put them on separate layers, it's just a really hard problem. But language just offers a really nice framework for getting a sample from a posterior as opposed to trying to do all of this in post-processing. But this doesn't actually stop for just Autopilot, right, John? This can be used for Optimus.
Yeah, I guess they wouldn't be called lanes, but you could imagine, sort of in this, stage here, that you might have sort of paths that sort of, encode the possible places that people could walk.
Yeah, it's basically if you're in a factory or in a, home setting, you can just ask the robot, okay, please route to the kitchen, or please route to some location in the factory, and then we predict a set of pathways that would go through the aisles, take the robot, and say, OK, this is how you get to the kitchen. It just really gives us a nice framework to model these different paths that simplify the navigation problem for the downstream planner.
All right, so ultimately what we get from this lane detection network is a set of lanes and their connectivities, which comes directly from the network. There's no additional step here for sparsifying these dense predictions into sparse ones. This is just the direct, unfiltered output of the network. OK, so I talked a little bit about lanes. I'm going to briefly touch on how we model and predict the future paths and other semantics on objects. So I'm just going to go really quickly through two examples. The video on the right here, we've got a car that's actually running a red light and turning in front of us. What we do to handle situations like this is we predict a set of short time horizon future trajectories on all objects. We can use these to anticipate the dangerous situation here and apply whatever braking and steering actions required to avoid a collision. In the video on the right, there's two vehicles in front of us. The one in the left lane is parked. Apparently, it's being loaded, unloaded. I don't know why the driver decided to park there. But the important thing is that our neural network predicted that it was stopped, which is the red color there. The vehicle in the other lane, as you notice, also is stationary. But that one's obviously just waiting for that red light to turn green. So even though both objects are stationary and have zero velocity, it's the semantics that is really important here so that we don't get stuck behind that awkwardly parked car. Predicting all of these agent attributes presents some practical problems when trying to build a real-time system. We need to maximize the frame rate of our object detection stack so that Autopilot can quickly react to the changing environment. Every millisecond really matters here. To minimize the inference latency, our neural network is split into two phases. In the first phase, we identify the locations in 3D space where agents exist. In the second stage, we then pull out tensors at those 3D locations, append it with additional data that's on the vehicle, and then we do the rest of the processing. This sparsification step allows the neural network to focus compute on the areas that matter most, which gives us superior performance for a fraction of the latency cost. So putting it all together, the Autopilot vision stack predicts more than just the geometry and kinematics of the world. It also predicts a rich set of semantics, which enables safe and human-like driving. I'm now going to hand things off to Sri, who will tell us how we run all these cool neural networks on our FSD computer. Thank you.
Thanks, Ron. Hi, everyone. I'm Sri. Today, I'm going to give a glimpse of what it takes to run these FSD networks in the car and how do we optimize for the inference latency. Today, I'm going to focus just on the FSD Lanes Network that John just talked about. So when we started this track, we wanted to know if we can run this FSD Lanes Network natively on the TRIP engine, which is our in-house neural network accelerator that we built in the FSD computer. When we built this hardware, we kept it simple, and we made sure it can do one thing ridiculously fast: dense dot products. But this architecture is autoregressive and iterative, where it crunches through multiple attention blocks in the inner loop, producing sparse points directly at every step. So the challenge here was, how can we do this sparse point prediction and sparse computation on a dense dot product engine? Let's see how we did this on the TRIP. So the network predicts the heat map of most probable spatial locations of the point. Now, we do a argmax and a one-hot operation, which gives the one-hot encoding of the index of the spatial location. Now, we need to select the embedding associated with this index from an embedding table that is learned during training. To do this on TRIP, we actually built a lookup table in SRAM, and we engineered the dimensions of this embedding such that we could achieve all of this thing with just matrix multiplication. Not just that, we also wanted to store this embedding into a token cache so that we don't recompute this for every iteration, rather reuse it for future point prediction. Again, we pulled some tricks here where we did all these operations just on the dot product engine. It's actually cool that our team found creative ways to map all these operations on the TRIP engine in ways that were not even imagined when this hardware was designed. But that's not the only thing we had to do to make this work. We actually implemented a whole lot of operations and features to make this model compilable, to improve the in-state accuracy, as well as to optimize performance. All of these things helped us run this 75 million parameter model just under 10 milliseconds of latency, consuming just 8 watts of power. But this is not the only architecture running in the car. There are so many other architectures, modules, and networks we need to run in the car. To give a sense of scale, there are about a billion parameters of all the networks combined, producing around 1,000 neural network signals. So we need to make sure we optimize them jointly and such that we maximize the compute utilization, throughput, and minimize the latency. So we built a compiler just for neural networks that shares the structure to traditional compilers. As you can see, it takes the massive graph of neural nets with 150K nodes and 375K connection, takes this thing, partitions them into independent subgraphs, and compiles each of those subgraphs natively for the inference devices. Then we have a neural network linker, which shares the structure to traditional linker, where we perform this link time optimization. There, we solve an offline optimization problem with compute memory and memory bandwidth constraints so that it comes with an optimized schedule that gets executed in the car. On the runtime, we designed a hybrid scheduling system which basically does heterogeneous scheduling on one SoC and distributed scheduling across both the SoCs to run these networks in a model parallel fashion. To get 100 TOPS of compute utilization, we need to optimize across all the layers of software, right from tuning the network architecture, the compiler, all the way to implementing a low latency, high bandwidth RDMA link across both the SoCs, and in fact, going even deeper to understanding and optimizing the cache coherent and non-coherent data paths of the accelerator in the SoC. This is a lot of optimization at every level in order to make sure we get the highest frame rate, and as every millisecond counts here. And this is the visualization of the neural networks that are running in the car. This is our digital brain, essentially. As you can see, these operations are nothing but just the matrix multiplication, convolution, to name a few, real operations running in the car. To train this network with a billion parameters, you need a lot of labeled data. So Egan is going to talk about how do we achieve this with the auto labeling pipeline.
Thank you, Sri. Hi, everyone. I'm Yegan Zhang, and I'm leading geometric vision at Autopilot. So, yeah, let's talk about auto labeling. So we have several kinds of auto labeling frameworks to support various types of networks. But today, I'd like to focus on the awesome Lanes Net here. So to successfully train and generalize this network to everywhere, we think we went tens of millions of trips from probably 1 million intersection or even more. So then how to do that? So it is certainly achievable to source sufficient amount of trips because we already have, as Tim explained earlier, we already have like 500,000 trips per day cache rate. However, converting all those data into a training form is a very challenging technical problem. To solve this challenge, we've tried various ways of manual and auto labeling. So from the first column to the second, from the second to the third, each advance provided us nearly 100x improvement in throughput. But still, we want an even better auto labeling machine that can provide us good quality, diversity, and scalability. To meet all these requirements, despite the huge amount of engineering effort required here, we've developed a new auto labeling machine powered by multi-trip reconstruction. So this can replace 5 million hours of manual labeling with just 12 hours on cluster for labeling 10,000 trips. So how we solved? There are 3 big steps. The first step is high precision trajectory and structure recovery by multi-camera visual inertial odometry. So here, all the features, including ground surface, are inferred from videos by neural networks, then tracked and reconstructed in the vector space. So The typical drift rate of this trajectory in car is like 1.3 centimeter per meter and 0.45 milliradian per meter, which is pretty decent considering its compact compute requirement. Then the recovered surface and road details are also used as a strong guidance for the later manual verification step. This is also enabled in every FSD vehicle, so we get pre-processed trajectories and structures along with the trip data. The second step is multi-trip reconstruction, which is the big and core piece of this machine. So the video shows how the previously shown trip is reconstructed and aligned with other trips. Basically, other trips from different vehicles, not the same vehicle. So this is done by multiple internal steps like course alignment, pairwise matching, joint optimization, then further surface refinement. In the end, the human analyst comes in and finalizes the label. So each heavy steps are already fully parallelized on the cluster. So the entire process usually takes just a couple of hours. The last step is actually auto-labeling the new trips. So here, we use the same multi-trip alignment engine, but only between pre-built reconstruction and each new trip. So it's much, much simpler than fully reconstructing all the clips altogether. That's why it only takes 30 minutes per trip to auto-label instead of several hours of manual labeling. And this is also the key of scalability of this machine. This machine easily scales as long as we have available compute and trip data. So about 50 trips were newly auto-labeled from this scene, and some of them are shown here. So 50 trips from different vehicles. So this is how we capture and transform the space-time slices of the world into the network supervision.
Yeah, one thing I'd like to note is that Jagan just talked about how we auto-label our lanes. But we have auto-labelers for almost every task that we do, including our planner. And many of these are fully automatic. There's no humans involved. For example, for objects, all of the kinematics, the shapes, the futures, everything just comes from auto-labeling. And the same is true for occupancy, too. And we have really just built a machine around this.
Yeah, so if you can go back one slide. One more. It says parallelized on cluster. So that sounds pretty straightforward, but it really wasn't. Maybe it's fun to share how something like this comes about. So a while ago, we didn't have any auto-labeling at all. And then someone makes a script. It starts to work. It starts working better until we reach a volume that's pretty high, and we clearly need a solution. And so there were two other engineers in our team who were like, hey, that's an interesting thing. What we needed to do was build a whole graph of essentially Python functions that would need to run one after the other. First, you pull the clip, then you do some cleaning, then you do some network inference, then another network inference, until you finally get this. So you need to do this at a large scale. So I tell them, we probably need to shoot for 100,000 clips per day, or like 100,000 items. That seems good. And so the engineer said, well, we can do a bit of Postgres and a bit of elbow grease. We can do it. Meanwhile, we are a bit later, and we're doing 20 million of these functions every single day. Again, we pull in around 500,000 clips, and on those, we run a ton of functions, each of these, in a streaming fashion. And so that's kind of the back-end infra that's also needed to not just run training, but also auto-labeling.
Yeah, it really is like a factory that produces labels, and like production lines, yield, quality, inventory, like all of the same concepts apply to this label factory that applies for the factory for our cars.
That's right.
Okay, thanks, Tim and Ashok. So concluding this section, I'd like to share a few more challenging and interesting examples for network for sure, and even for humans probably. So from the top, there's like examples for like lack of lights case, or foggy night, or roundabout and heavy occlusions by parked cars, and even rainy night with the raindrops on camera lenses. These are challenging, but once their original scenes are fully reconstructed by other clips, all of them can be auto-labeled so that our cars can drive even better through these challenging scenarios. So now, let me pass the mic to David to learn more about how Sim is creating the new world on top of these labels. Thank you.
Thank you, Yagan. My name is David, and I'm going to talk about simulation. So simulation plays a critical role in providing data that is difficult to source and/or hard to label. However, 3D scenes are notoriously slow to produce. Take, for example, the simulated scene playing behind me. A complex intersection from Market Street in San Francisco. It would take 2 weeks for artists to complete. And for us, that is painfully slow. However, I'm going to talk about using Yagan's automated ground truth labels along with some brand new tooling that allows us to procedurally generate this scene and many like it in just 5 minutes. That's an amazing 1,000 times faster than before. So let's dive in to how a scene like this is created. We start by piping the automated ground truth labels into our simulated world creator tooling inside the software Houdini. Starting with road boundary labels, we can generate a solid road mesh and retopologize it with the lane graph labels. This helps inform important road details like crossroad slope and detailed material blending. Next, we can use the line data and sweep geometry across its surface and project it to the road, creating lane paint decals. Next, using median edges, we can spawn island geometry and populate it with randomized foliage. This drastically changes the visibility of the scene. Now, the outside world can be generated through a series of randomized heuristics. Modular building generators create visual obstructions, while randomly placed objects like hydrants can change the color of the curbs, while trees can drop leaves below it, obscuring lines or edges. Next, we can bring in map data to inform positions of things like traffic lights or stop signs. We can trace along its normal to collect important information like number of lanes and even get accurate street names on the signs themselves. Next, using lane graph, we can determine lane connectivity and spawn directional road markings on the road and their accompanying road signs. And finally, with lane graph itself, we can determine lane adjacency and other useful metrics to spawn randomized traffic permutations inside our simulator. And again, this is all automatic, no artists in the loop, and happens within minutes. And now this sets us up to do some pretty cool things. Since everything is based on data and heuristics, we can start to fuzz parameters to create visual variations of the single ground truth. It can be as subtle as object placement and random material swapping to more drastic changes like entirely new biomes or locations of environment, like urban, suburban, or rural. This allows us to create infinite targeted permutations for specific ground truths that we need more ground truth for. And all this happens within a click of a button. And we can even take this one step further by altering our ground truth itself. Say John wants his network to pay more attention to directional road markings to better detect an upcoming captive left turn lane. We can start to procedurally alter our lane graph inside the simulator to help to create entirely new flows through this intersection to help focus the network's attention to the road markings to create more accurate predictions. And this is a great example of how this tooling allows us to create new data that could never be collected from the real world. And the true power of this tool is in its architecture and how we can run all tasks in parallel to infinitely scale. So you saw the tile creator tool in action, converting the ground truth labels into their counterparts. Next, we can use our tile extractor tool to divide this data into geohash tiles about 150 meters square in size. We then save out that data into separate geometry and instance files. This gives us a clean source of data that's easy to load and allows us to be rendering engine agnostic for the future. Then, using a tile loader tool, we can summon any number of those cache tiles using a geohash ID. Currently, we're doing about these 5x5 tiles or 3x3, usually centered around fleet hotspots or interesting lane graph locations. And the tile loader also converts these tile sets into U assets for consumption by the Unreal Engine and gives you a finished product from what you saw in the first slide. And this really sets us up for size and scale. And as you can see on the map behind us, we can easily generate most of San Francisco city streets. And this didn't take years or even months of work, but rather 2 weeks by one person. And we can continue to manage and grow all this data using our PDG network inside of the tooling. This allows us to throw compute at it and regenerate all these tile sets overnight. This ensures all environments are of consistent quality and features, which is super important for training, since new ontologies and signals are constantly released. And now, to come full circle, because we generated all these tile sets from ground truth data, they contain all the weird intricacies from the real world, and we can combine that with the procedural, visual, and traffic variety to create limitless, targeted data for the network to learn from. And that concludes the sim section. I'll pass it to Kate to talk about how we can use all this data to improve autopilot. Thank you.
Thanks, David. Hi, everyone. My name is Kate Park, and I'm here to talk about the data engine, which is the process by which we improve our neural networks via data. We're going to show you how we deterministically solve interventions via data and walk you through the life of this particular clip. In this scenario, autopilot is approaching a turn and incorrectly predicts that crossing vehicle as stopped for traffic, and thus a vehicle that we would slow down for. In reality, there's nobody in the car. It's just awkwardly parked. We've built this tooling to identify the mispredictions, correct the label, and categorize this clip into an evaluation set. This particular clip happens to be one of 126 that we've diagnosed as challenging parked cars at turns. Because of this infra, we can curate this evaluation set without any engineering resources custom to this particular challenge case. To actually solve that challenge case requires mining thousands of examples like it, and it's something Tesla can trivially do. We simply use our data sourcing infra, request data, and use the tooling shown previously to correct the labels. By surgically targeting the mispredictions of the current model, we're only adding the most valuable examples to our training set. We surgically fix 13,900 clips, and because those were examples where the current model struggles, we don't even need to change the model architecture. A simple weight update with this new valuable data is enough to solve the challenge case. So you see, we no longer predict that crossing vehicle as stopped, as shown in orange, but parked, as shown in red. In academia, we often see that people keep data constant, but at Tesla, it's very much the opposite. We see time and again that data is one of the best, if not the most deterministic lever to solving these interventions. We just showed you the data engine loop for one challenge case, namely these parked cars at turns. But there are many challenge cases even for one signal of vehicle movement. We apply this data engine loop to every single challenge case we've diagnosed, whether it's buses, curvy roads, stopped vehicles, parking lots. And we don't just add data once, we do this again and again to perfect the semantic. In fact, this year, we updated our vehicle movement signal 5 times, and with every weight update trained on the new data, we push our vehicle movement accuracy up and up. This data engine framework applies to all our signals, whether they're 3D, multicam video, whether the data is human-labeled, auto-labeled, or simulated, whether it's an offline model or an online model. And Tesla's able to do this at scale because of the fleet advantage, the infra that our eng team has built, and the labeling resources that feed our networks. To train on all this data, we need a massive amount of compute, so I'll hand it off to Pete and Ganesh to talk about the Dojo supercomputing platform. Thank you.
Thank you, Katie. Thanks, everybody. Thanks for hanging in there. We're almost there. My name is Pete Bannon. I run